Hey y'all, sorry for not being there again. Today, you're going to go through these notes. You should have the note packet and a summary page. That summary page is going to be right next to the notes because we're going to refer to that actually throughout rather than just at the end to take like summarizing notes as we go through some of these problems. But the first thing I want you to do is to try the warm-up questions 1 and 2. Make sure that you refer back to your notes if you need to or each other. Okay, please pause this video here, try these on your own, and then come back and check your answers. Okay, so I hope that you were able to check your answers or try this on your own, and you can check your answers here. There is no stretch on either of these, but the second one does have a reflection, so those points do get flipped of where they are going. Okay, so in what we did last class and in those 2 warm-up problems, they were all transformations of the parent function, 1 over x. Okay, so that's like the typical transformation form, parent function, 1 over x. But when we talk about what the word rational means, rational, if you're talking about a number, is a ratio of integers. So that's why we have a fraction. You can have integers like 2 divided by 3. And then when we talk about functions, it's a ratio of polynomials. Now, x is a polynomial when it's by itself of just degree 1. But not every time will the polynomial be degree 1 of just x. So you can see down here lots of examples. So we have the typical 1 over x. But then in the numerator, since it is a ratio of polynomials, you can start having polynomials in the numerator and the denominator. Okay, both of these have degree 1. Then we have an example where we have a polynomial x minus 4 with degree 1 in the numerator, and then a polynomial with an x degree of 3 in the denominator. Sometimes we can have 2 and 2. Okay, sometimes we can have the numerator degree bigger than the denominator degree. So we have lots of different examples. Sometimes the numerator is smaller than the denominator in these 2 instances, and then sometimes the degree equals each other in the numerator and denominator in these 2 examples. And then sometimes we even have the degree in the numerator bigger than the denominator. And the degree of those numerators and denominators do impact the graph. Okay, and so if we can, we're going to try and put them into the transformation form, but not every time will we be able to do so. And so if it's not able to do so, we have to know how those degrees actually affect our graph. And that's what these notes are going to explore. So how the equations affect the graph, and then hopefully once you know all of the effects, you'll be able to then put that information onto the graph. So for each one of these, it's going to kind of be like an I do one, you do one type of thing. So each page goes through a different type of example. Okay, so first example, when I look at the function of 3x minus 1 divided by x minus 2. Okay, the first thing that I want you to start looking at is what is the degree in both the numerator and denominator. So the degree in the numerator is 1 because of the 3x, and it's also 1 in the denominator because of the x minus 2. So when the degrees in the numerator equal the degree in the denominator, this is how we're going to approach it. Okay, we are going to want to try to rewrite the function in that transformation form. Now it says long division, but you can use the box if that's something you prefer, which I do. So I'm going to actually divide this fraction exactly as it tells me to. So taking 3x minus 1 and dividing by x minus 2, I need to get a 3x to show up, so I need to multiply by 3. This gets me to negative 6. But since I need a negative 1 to be in the problem, I need to add 5, which means this is my remainder. So what does this actually mean? Okay, this means that x minus 2 times 3 with a remainder of 5 over x minus 2 equals 3x minus 1 divided by x minus 2. Or excuse me, equals 3x minus 1. And so when I say this, the reason I want to talk about when I divide this, what I just came up with as my solution is going to be the same exact equation. Okay, so 3 plus 5 divided by x minus 2 is actually the same exact thing as what we wrote up there. So 3 plus 5 over x minus 2. Okay, and this equaled 3x minus 1. So we are taking what, when we divided 3x minus 1 divided by x minus 2, whatever we get as our answer, that is actually the equivalent equation. And that is the equation we're going to want to use when we graph, because we just actually put it into the form of our k plus a divided by, x minus h. So if we're able to divide the polynomials, we can try and turn them into our transformation form. And if we turn it into our transformation form, we now have enough information to graph it. So we know our vertical asymptote is x equals 2, and we know our horizontal asymptote, also known as our end behavior asymptote, is y equals 3. And then do we have a stretch? Yes, we have a stretch of 5. So the fact that we are able to divide it, we can put it in the form, answer the questions like we did in the warm-up in last class, and put all of this information on our graph. You also can calculate the x-intercept on the left-hand side, which I will do before I graph it. So remember, anytime you need to calculate an x-intercept, substitute y for 0, and then 3x minus 1 divided by x minus 2. Now the reason I'm using the original rational function instead of the transformation form is because now when I have divided by x minus 2 and I need to multiply both sides by x minus 2, that's going to make that divide out, and then 0 times anything is just 0. So what's going to happen is that 0 is simply just going to equal whatever the numerator is every time. Because every time I'm going to multiply both sides by the denominator, and it's going to cancel, divide out. So I know that my x-intercept is going to be 1/3. Okay, so that will also help you check your graph. So I'm going to go ahead and graph my vertical asymptote at x equals 2. My end behavior asymptote at y equals 3. I know I need a stretch of 5, so instead of going 1, 1, I now go 1, 5. 1, 2, 3, 4, 5. And I also do that on the left. Okay, and instead of going to a half, if I multiply a half by 5, I go to 5 halves. 1, 2, 1, 2, oops. 2, 1, 2 1/2. 1, 2, 1, 2. And instead of going 1/2, 2, I go 1/2, 10. But to go up that many would be too many. So if I go 3, it should be all the way down at 7 here. Okay, and you can also check that you should have an x-intercept of about 1/3. So when I actually plotted that, we'll go right through the x-axis at 1/3, come up here, and glide through. So sometimes you won't get the exact points, those 3 points on each side, but you could figure it out. Because if I went over 5, remember, if I go to the right 5, I'm supposed to go up 1/5 because it's the reciprocal, so I can multiply. So really, if I go over 5, I should be going up 1, so there should be a point right there. Okay, so now I would like you to try the second one. Okay, and then come back here. Okay, hopefully you were able to get through that on your own, and you could check your answers here. So both of the degrees of the numerators are the same, so they're both 1. And then if you were able to divide the polynomials, 4x plus 1 divided by x minus 4, you end up getting 4 plus a remainder of 5. And so you write that as 4 plus remainder 5, all divided by x minus 1. And that is your transformation form. So you're able to graph it. Okay. So in both of these, something very specific happened that we need to highlight. Okay, in both of these, the degrees, I wanted to highlight, not write it in. Okay, both of these degrees were equal. So it doesn't matter that they're 1, it matters that they're equal. Okay, why does that matter? Because there is a relationship. If the degrees of the numerator and denominator are the same, there is a relationship between what this end behavior asymptote is going to be and the original rational function. So if we look here, when the degrees are the same, where do you see the 3 show up in question number 1? Or where do you see the 4 from the end behavior asymptote number 2 show up in number 2? It shows up when you divide those coefficients, even though it is just 3 divided by 1 or 4 divided by 1, it is the division of those. So when our degrees are the same in the numerator and denominator, our end behavior asymptote is always going to be the coefficients of those degrees, those leading coefficients, divided by each other. Okay, and so I want to write that in that summary page that you have off to the side. So bring that summary page over in here. And so we're talking right now here. So when the degree of the numerator and the degree of the denominator is the same, our end behavior asymptote, so those are, remember, are the same thing as horizontal, if they're horizontal lines, is if you divide the leading coefficients. So even if both degrees are 5, and you have for instance, like x to the 5th divided by x to the 5th, but let's say your leading coefficient is 15, and your leading coefficient of this one's -3, that would mean my end behavior asymptote is y equals -5, because I would divide the 15 then the -3. Okay, so that's going to happen every time the degrees are equal. And we're going to then notice that on each page we're going to have something different happen with the degrees. It's either going to be less than or greater than, and that will tell us something very specific about the graph itself. Okay, let's go back to the notes. Okay, so on the next page, the graph's already done for us. This way, it's just easier for us and faster for us to start to see how we deal with something, how we deal with an equation when you can't divide it, and when our degrees are different. Okay, so looking at question number 3. Right away, I can see that my degree in the numerator is 0 because there's no x term. The degree in the denominator is 2, so thus the numerator degree is smaller than the denominator degree. Okay. Now, could you divide 3 divided by x squared minus 1 if I tried to do that? Could I get a 3 to show up out of an x squared? And no, I can't divide. Okay, so that's what this question is asking. Can you use division? No, you can't get 3 times nothing is going to, excuse me, other way. X squared times nothing is going to get you that 3, so you're not able to do that. Okay, so if we can't divide it, how are we going to start graphing these functions? Because it's not in transformation form, as you can see. Yes, we have a 3. That could be an a value, if you think about it, but the fact that we have an x squared in the denominator, this is no longer transformation form. So let's look at how the graph has our asymptotes. Okay, so this should look very different than the graphs that we've been doing together. As you can see, if I zoom in here, we have 3 lines showing up. We have the left side, we have the right side, and we have the middle. And that is because we end up having two vertical asymptotes. We have the dotted line here at x equals -1, and we also have the dotted line here at x equals +1. So those are two of our asymptotes. X equals 1, x equals -1. We also have another dotted line at y equals 0. So this time we have two vertical asymptotes, one horizontal asymptote. Okay, let's see if we can make those numbers show up in our equation somehow. Well, our equation 3 divided by x squared minus 1, we weren't able to divide it, but could we factor it instead? So if we factor the denominator, okay, we can use our difference of squares pattern. X squared minus 1 turns into x plus 1 and x minus 1. And what do you know? Here it shows up that our asymptotes of 1 and -1 are in the denominator again. When it's x plus 1, we get an asymptote of -1, and when it's x minus 1, we get our asymptote of +1. So if we have two different binomials in the denominator, rather than in transformation form we just had one binomial, we could have two asymptotes. And if we have two vertical asymptotes, both of them need to show up in the domain. So we're going to actually make two jumps. We'll go from -infinity to -1, and then we'll go from -1 to 1, and then we'll go from 1 to infinity, because we have to make a jump each time that the x value cannot exist. So it can't exist at -1, and it can't exist at +1, so we have to include that in our domain. Okay, pause this video, answer the questions in number 4, and then we'll come back to try and make the conclusion about what happens for the asymptotes and how it relates to the degrees. Okay, welcome back. Hopefully you saw that the degree in the numerator is smaller than the degree in the denominator again, so we're not able to divide this out. So if we can't divide out, we need to get everything factored as much as possible, because those factors are what is going to help us figure out our asymptotes. And for future classes, what's called a whole. So when you factor that denominator, you get x squared plus 2x minus 8, which is the factor of x plus 4 times the factor of x minus 2. And then you can see from the graph that the x minus 2 created an asymptote of x equals +2, because we always are going to do that inverse. And then the factor of x plus 4 gives us the vertical asymptote of x equals -4. So we are going to start setting our denominators equal to 0 to find our vertical asymptotes. So you can see that happening in both of these cases, that if you take each factor and set them equal to 0, really solving the denominator equal to 0, that's what's going to get our vertical asymptotes every time. This end behavior asymptote might have thrown you for a loop. That's why I put a because you don't really see a dotted line going horizontally. And you also see this middle section, this line, kind of going through the center. And so how is it possible to have an asymptote if we're going through the center like this? Well, that's why we call it an end behavior asymptote. So this is the first time where we're actually crossing what we consider to be the asymptote. Okay, because an end behavior asymptote is going to be more true as the x gets very large in both the positive and negative direction. Where are we approaching? So it's not necessarily in the center. It's as x gets large, in both the positive and negative, where is this asymptote approaching? So as x gets larger on the right, it is approaching 0, and as x gets larger on the left, aka smaller, it is approaching 0. So we still have an end behavior asymptote of y equals 0. It's just in rare cases that because it's approaching 0 on the left and the right, the center can actually go through it. It's a little bit of a confusing aspect, but it can happen in sometimes like this. Okay, so sometimes you'll see that if you have two vertical asymptotes, the middle section will go through it in like this almost cubic looking function. Sometimes you'll have like a parabola in the center. Sometimes the two ends will be on the same side of the asymptote, like in question 3. Sometimes they'll be opposite, like in question 4. In this class, we're not going to concentrate so much on the graphs, like graphing ones like this, or knowing when that's going to happen, of when it's going to cross through. What we want to concentrate on more is how do we find where the asymptotes are. So in both of these cases, we had the degrees of the numerator smaller than the degrees of the denominator, because we had 1 and 2 and 0 and 2. And in both of these cases, you may have noticed that y equals 0 showed up as the end behavior asymptote. And that is going to happen every single time the numerator degree is less than the denominator degree. So we're going to go ahead and put that in our summary page. So when the degree of the numerator is smaller than the degree of the denominator, so numerator is smaller than the denominator, it is always going to give you a y equals 0 and behavior asymptote. You don't have to worry about doing any division. You don't have to worry about figuring out what numbers in the equation to use. You're just always going to have y equals 0 as the end behavior asymptote when the degree in the numerator is smaller than the denominator. Okay, going back to the notes on the last page. Hopefully you'll be able to kind of take a guess at what's going to happen for these degrees. And you can also see the difference in the graphs of these two graphs. So when you look at the degrees, okay, I have a degree 2 in the numerator, degree 1 in the denominator. So this time my numerator is bigger than the denominator. Okay. Same thing that's happening in number 6, 2 and 1. So the numerator is bigger than the denominator. Hopefully you're seeing something different about this graph. There is a dotted line on a diagonal in both of these. We no longer have what we call the horizontal asymptote, which is why we call it the end behavior asymptote, because it's what's happening to the function on the ends. Okay, as the graph goes to the right, what's happening to that value of the function? As the graph goes to the left, what's happening to the value of the function? So that is going to happen every time when we have the numerator, the degree larger than the numerator and the denominator larger. We're going to have this diagonal line, which is called a slant asymptote. Okay, it's going to be called a slant. Now we have to figure out where in the world are we going to find out where this slant comes from. And that's what these questions are going to go through for us. So that's how these graphs are different. So we have no horizontal asymptote. But a slant. Okay. So can we divide it to figure out if there's like a transformation form? So let's see if we can divide it like we did in questions 1 and 2. Okay. So I need to divide by x plus 1. See if I can get x squared. Okay, I can get x times x is x squared, and then I have a 1x. But I don't want it to be anything with an x because I just want x squared to show up. So I do need to subtract 1x to make sure I get 0x, because there is a 0x in the problem, technically. And then this would be a minus 1, and then this would be a negative 1. And then I do not want a negative 1 to show up because I want a plus 0 at the end, so I do need a remainder of 1 to show up. So, well, what does that mean? Okay, that means that I know x plus 1 times x minus 1, but with a remainder of 1, shows up to equal x squared. And how does that help me? Well, what just happened is that when we divided this and we had this equation show up as the x minus 1 part, let's see if this shows up somewhere on our graph. Looking at the graph itself, our vertical asymptote is x equals -1. Okay, that comes from the denominator of the original function, x plus 1. But then we have a y equals, if I zoom in here, my y-intercept is -1, and my slope of this line, up 1 over 1, up 1 over 1, is just 1. So I have 1x minus 1. And if you notice, this equation was what I got when I divided my function. Okay. And that is going to be how we find our slant. When we end up dividing the two polynomials together, if it doesn't turn into transformation form, and yet we have this linear equation left for, or not, excuse me, linear equation, this binomial instead of a constant show up, that is our slant asymptote. Okay, so when we divide whatever, we end up with our quotient, that is going to be our slant asymptote, or our end behavior asymptote. Okay, so go ahead and try the next one and see if you can get the equation of the slant asymptote from the graph and see if you can get it to show up when you divide. Pause this video now. Okay, welcome back. Hopefully you were able to divide this out and notice that when you divide x squared minus 2x minus 3 by x plus 2, you end up with the quotient of x minus 4 and a remainder of 5. And so anytime your quotient ends up being this linear piece, that is going to be the equation from our slant asymptote or end behavior asymptote. So the x minus 4 is our quotient, and so that's the equation of the line that is on the diagonal. And that is going to happen every time our degree of our numerator is bigger than the degree in our denominator. So let's put that on our summary page. So when the degree of the numerator is bigger than the degree of the denominator, we're always going to have what we call a slant. So you need to divide, okay? Use division. And it's going to be y equals whatever the quotient is. Okay? And then every time to find our vertical asymptotes, we solve for the denominator equal to 0. So if I have like an x plus 4 and an x minus 3, I would have x equals -4 and x equals 3. And then anytime I need my intercepts, it just is a little different depending if you're looking for x-intercepts. Remember, we set y equals 0, and we solve for x. If we're looking for a y-intercept, we set x equal to 0, and we evaluate. So, if you're able to find all of the pieces of information, you need the asymptotes, both vertical and end behavior. You need your x-intercepts and y-intercepts. Then you could put it all on your graph. And most of this time, you would just, if you needed to find more points beyond your x-intercepts, hopefully you can get it in transformation form to find your a value, or just use the a value, use the equation to substitute in more points. Okay, what I would like for you to do is just try and answer these 3 questions on the bottom to see if you understood the point of today's notes. And in the homework, you'll answer questions like this, and you'll then try to put it all together on a graph. All right, thanks guys. I will see you next class. Just pause the video here and come back to check your answers. All right, everybody, here's your answers. Hopefully you'll notice number 3, you had to find a slant. Whatever you get for your quotient is your slant. There's actually no x-intercepts because you would have to solve x squared equals -3, and we don't have complex x-intercepts. And yeah, okay, now's your time to go ask for a copy of the homework. Thanks.